Okay, sorry. So I got past that call, so here we are. So what we've developed, the fundamental equations that we've developed and in which everything will be based have already been done. So let's summarize them. The first one, well, the last one done, but I'll try to write on top of it, maybe that'll clarify them even more, or somewhat. The covariance function of the output is given by CD, AD to the I, covariance of the state, CD transpose, provided that I is not zero. The covariance of the output for zero lag is equal, that is with itself, CD, covariance of the state, CD transpose, plus R, which is the covariance of the noise. Okay? And before that, we derived an equation that said that the covariance of the state was equal to AD times the covariance of the state times AD transpose plus the covariance of W. Okay, that's it. That's what we got. From there, we're going to do everything. I think you should, if you can, take a little time, because this is easy, take a little time and sort of derive yourself these three equations. As you can see, there's not much to it except to get the y at k plus I and so on. But you know, these three expressions is what the stochastic identification scheme that we are about to present are based on. So here comes the punchline. If you look at the correlation function of the output, because this is, remember, this is the expected value of y at k plus I with y at k transpose. In other words, this is something that we can calculate from the output, right? If we have a long enough output, we can find what is this, well, we can estimate what this expectation is, right? Just from the output. You take the output, shift it, do it, and so on, right? So this is available. That's available. In fact, we are going to turn our data. The first thing that we do in a stochastic identification with this scheme is we take our output data and we convert it into this, okay? Into the correlation of the output for various lags. Now, this can be written like this. CD AD times parentheses I'm sorry, AD I minus 1, take one of the ADs away from here, and then I get AD covariance of the state CD transpose. Boy, I don't know, I can't fit things correctly today. Wanted to have it cleanly somewhere. I guess I'll just erase this and put it back when needed, because I want this to come clean. So I'm going to write as CD AD to the I minus 1 times, I'm going to put a parenthesis, the AD that we just took out times sigma times CD transpose. okay, for I not equal to 0. So, if you look at that equation, none of them work. If you look at that equation and you remember the Markov parameters yj, when we know the input, the Markov parameters are CD AD to the j minus 1 times BD, right? Now comparing the expression of the Markov parameters to this, we can see that we can take the output correlation to be Markov parameters of a system that has the same C as the system, the same A as the system, and this product replaces the B. Therefore, I can take my algorithm that I developed for known input, and by the time, what was this thing that we did when we had known input? The first step was to calculate the observer Markov parameters. The second step was to extract from the observer Markov parameters the Markov parameters, right? Well, here we start with, we get the Markov parameters without any observer Markov parameters. We get the Markov parameters from the correlations of the output, and that's it. From that point onward, we form the Hankel matrices in exactly the same way, no need to change anything, right? On the Hankel matrices, and we extract the realization of the system, as I explained in the lecture on the ERA, in exactly the same way, except that when we get the C, it is the C, when we get the A, it is the A, but when we get the B, is not the B, is AD sigma CD transpose, because it doesn't make sense to talk about what is the B, right? In essence, that is the end of the stochastic ID, because now at this point you can say now how many Markov parameters do you need? Well, if you need to get 100 Markovs, that means that you need to get the correlation of the output to the 100th lag, okay? If you need 300, you need to do it to 300 and so on. Now, because this is based on expectations, remember these formulas are all expectations. In order for them to be reasonably accurate, you have to have a long signal, right? So the longer the time that you collect the output, the better. Typically, in the example that I think I've been doing, I have either half an hour or 1 hour of data, right, at 0.02 seconds or something like that, in order to make these averages converge accurately, okay? As I say, after this point, the Hankels H0 and H1 are done exactly the same as before, so you don't need to code anything new. And the ERA, that is extracting the matrices using ERA, same. So all there is to the stochastic identification in its basic form, or in this algorithm, is simply that the output correlation covariance takes the place of the Markov parameters, and it has this form. Now, one question that sometimes arises is to whether one could calculate the Q and the R. I have actually looked at it. They're not particularly useful as far as I know, the Q and the R, but if you remember, we know, at least from a formality point of view, we know that the correlation of the output covariance with itself at 0 lag is equal to CD, it's this, right? I'm sorry, CD sigma, CD transpose plus R. So this is, now of course this is computable from the data, and it's equal to this. Now because we know G, or let's say this is known from the ID, right? Let's say we call it G. So that matrix, which we normally would call B, right? We call G, not to confuse it with B, because there is no B. So if this is G, you can see that AD multiplied times sigma times CD transpose is G. Therefore, it follows that sigma times CD transpose is AD to the minus 1 times G. So this is computable, right? Now that means that sigma CD to the minus 1, which is here, can be replaced by this. And therefore you can write that the output covariance at 0 is equal to CD multiplied times this, which is AD to the minus 1 times G, right? CD times this, which is AD to the minus 1 times G plus R. Now, CD is known, AD to the minus 1 is known, and G is known. Therefore, it follows that conventionally the covariance of the noise is identifiable, or of the right term in the measurement equation, is identifiable as the covariance of the output minus this, right? CD AD to the minus 1 G. Now, the reason why I say this is nominal, it's because, for example, it turns out that typically R is very small compared to this. So R tends to be very small compared to the covariance of the output at 0, because the noise is a tiny amount compared to this. At least for the case where we are measuring, I shouldn't say that. It's small if there is no D, right? If it's just measurement noise. So if this is a big number that we have to subtract another big number to get a really small number, it's very difficult to get. This thing would have to converge so accurately. So usually, unless there is a D, the R that you get from plugging in this here is not necessarily that accurate, okay? Now, needless to say, it is not necessary to know what that R is. It's just kind of a curiosity or curious interest to know that, unless the purpose was to do something about a D, but that's not what we're doing here, okay? So this concludes the theoretical part of the stochastic identification. Now, what I cannot do well, because as I say, I don't have access to the laptop to show you, but I can make up for it in a different way, is to point out how is it that you get lambda I. So let me discuss it first, kind of like in practical terms, and then discuss a little bit what you actually do in MATLAB. So let's say that you have the output, and that the output was, let's say you were measuring two things, like that. First channel, second channel, right? Now, this could be 150,000 steps, whatever, right? So this is, not n because we're using that for order, but let's say L. So this is 1 and this is L, right? So you have L, and L could be 100,000 or something, as long as possible. You can't get too long. The longer the better. So now you want to calculate what is y at k plus 1 with y at k, expected value, right? Y at k plus 1 with y at k. So y at k plus 1, let me call this A, B, C, D, because that's all I need for these purposes, right? So y at k plus 1, starting from the beginning, would be the matrix starting in C and D, and then it goes all the way to L, right? So this now has how many points? Since you took the first column off, that has L minus 1 in them, right? That has L minus 1 in them. Now, that's yk plus 1. So yk plus 1, like that here, C, D, to the last point, multiplied times yk transpose, right, is like this. Now they have to be the same size, right? So that means that this one comes with A and B, right? C and D, and it goes like that. And then we have to kill the last value. So here we have the L minus 1 term, right? Now we multiply all of this times all of this and divide by L minus 1. So all of this row times all of this column added together divided by L minus 1 would be the number here, right? All of this column times all of this column added together divided by L minus 1 would be this point here. All of this row times all of this column here, all of this row times all of this row here. All of them divided by L minus 1. So that would be the expected value of this at 1 lag. At 2 lags, that means that we'd have to start on the third one here, right? Instead of CD, this would become EF, right? So we would have to start with E and F till the end, and then when we put this one here, we would have to stop at L minus 2, right? Same thing again. And now we divide by L minus 2, and so on. So this is obviously the definition of expectation. Now, if we are going to do that all the way to how many, we need the number of lags that we do is the number of Markov parameters that we have to form the Hankel matrices. So if we decide we want 400 Markovs, then we need to do this up to cutting off 400 entries from here, right? We're going to start 400 from here and we're going to cut 400 from the end. So in order for this 400 to be irrelevant for the computations, that means that your length should not be 1,000. Your length should be 50,000, right? So if you have 50,000 points and you're cutting 400 to get the Markovs, that means that every time you have something quite long to get the correlation. So that's fine, right? Now, you could write a little code to do this multiplication, shift, cut, shift, cut, shift, cut, and so on. But there is really no need, because MATLAB, I mean, you can do it and it might be useful to do it anyway for the educational value of it, but there is a function in MATLAB which is called COVF, I think, covariance function, that does exactly what we're talking about. So, the covariance function in MATLAB, the only thing is, if you go to MATLAB and you say help, COVF, I think it is, then you'll get what I'm talking about regarding the fact that what you have to do is sort of reorder it. So you get, when you put the covariance function of your output, MATLAB is going to give you the results. but those results are not necessarily sort of in the standard exact format that you want to take the markup, so you have to do a little reorganization, okay? Now, I'm sure that you could figure it out yourselves, but I'm going to post in Blackboard the little MATLAB code that extracts the Markov parameters from output data that I use, so that if you want to guide yourself in case you need to, you can look at that one, okay? Now at this point, I haven't decided. I mean, I've taped essentially two lectures. I haven't decided whether I will do a third or not. It may be better perhaps to just leave it at this regarding new information, and to dedicate that time to think about useful practice homeworks and the potential research, so that I can send you or give you something in Blackboard that that will move us further along than perhaps another theoretical lecture, because this concludes everything that is theoretical regarding the fundamental design, identification with output only, right? With output only signals. So let me do that, and needless to say, if I do add something else, it'll be obvious because I will put it in the announcement in Blackboard. Okay, now, yeah, so we'll see each other when I'm back.